Okay, I'm trying to get out of this field of quantum electrodynamics or quantum physics with QCD. Um, this is going to be an easy and a difficult lecture at the same time. I want to critique, very popular books on quantum theory, which I think are inspired by some religion. I'm going to do so by talking about Feynman's strange theory of light and matter. Let me look. It's a book that still sells very well. Yeah, that's the inspiration for the but let me Google it. This little booklet, QAD, The Strange Theory of Light and Matter. It was the last book that Feynman wrote. I see that even despite the fact that this is a newer edition of this item, there's only one left in stock. I think that's not a bad thing. On my blog, readingfeynman.org, I left a number of critical remarks in 2015, so that's almost 10 years ago. They did not get destroyed by the dark force. My website got torn down by the DCMA because they said you copy things that you shouldn't copy. Same thing a little bit with trying to engage with Wikipedia authors and editors. There are dogmas, and so I just want to be bold. I read this book my daughter gave to me, How to Thrive as Your Most Vibrant, Weird, and Real Self. And so that's what I'm doing. Going back to the critique I want to do, it's it's a booklet, and I say that actually in let me see here my appraisal of it. I don't have it, but it's sort of it would be like a mandatory reading in the sense that what he uses in terms of metaphors. Is brilliant, the idea of a clock. Then two or three times talk about 5 months, wives, and other partners in crime. But in the end, I don't know. I'm not gonna look it up again. It is a bit cargo code science in the sense that the building blocks that he uses in this booklet, which probably I think it was written a long time ago. I don't think he reviewed it. I mean, passages like the alpha, the fine structure constant, is like a number given by God, and we don't know how he pushed his pencil. I seriously think that Feynman would have objected to the use of such language. But the building blocks in his theory are quite fine. We talk about the theory of light and matter, and his theory is rather strange, and that's what I want to talk about. I think it's not so strange. But we have a photon, we have an electron, and the photon will go from A to B. And an electron, is in some kind of atomic or molecular orbital and will also go from A to B. And then if the circumstances are such that the point B for the photon and the electron are the same, so if the photon and the electron happen to be at the same place, which I here vaguely describe by a delta x vectorized, a small three-dimensional space, at some time t, what is then the probability of interacting? That's what we're talking about. So I think he usefully decomposes the probability of a photon to go from A to B, of the electron to go from A to B, based on various models of an electron in free space, in hydrogen atomic orbital, in a molecular orbital. We're talking about Schrödinger's equations there. And then what sort of apparently when they are at the same spot, it's not necessarily an interaction. Maybe this is the model I have, and which I presented in the previous model, is that if you have a photon coming in, hitting an electron, which in our model we design as a ring current, some theta-beweging charge with the classical or Thomson radius tittering or moving around. In my previous lecture, I said, well, it's not, we cannot exclude that, an incoming photon would interfere with, the enormous electromagnetic field inside of the ring current, and then, change that field and change the motion of the electron for a while, and then it comes back into some equilibrium situation. Yeah, maybe not. I mean, in this model, we only have, an incoming photon here in this situation interacting with the charge itself and being reflected in what is probably a Thomson scattering process where no energy gets lost because the electron is firmly bound into some atomic or molecular orbital, and it returns back to its equilibrium situation. There is no formation of an ionic structure. No, it just pushes back. It does not absorb any thermal energy or whatever energy. And I would think that's the picture where basically, the photon and the charge interact. So not the electromagnetic field that keeps the charge in its orbit. But going back, it's sort of so that's where I think he got it right in that popular book. There's an amplitude or a probability for a photon to go from A to B. I don't agree with his path integral approach, where he says that a photon can have any velocity. It's not necessarily c. It can be somewhat less or somewhat more, or a lot less and a lot more. A photon is what it is in my theory. It's a point-like particle with an oscillating electric and magnetic field vector. And the electric and magnetic field vector are zero everywhere except for the point xt where the photon happens to be, and it's really remarkable because the photon can be at a point where the electric field vector and the magnetic field vector are zero, and then they can be at some position in between or at a max for the electric field vector, and equally a max for the magnetic field vector. whose magnitude is 1 over c times the magnitude of the electric field vector, and is perpendicular to it. That's why it's kind of difficult to write things like what I wrote, E plus B. We have the Lorentz formula, which says the force will be Q times the electric plus the velocity vector squared cross product times the. So the force formula is very complicated, and you cannot use easy geometric algebra. You need to constantly talk about mathematics in terms of bivectors, which isn't easy. But so that's the critique I had on, and I'm happy it didn't get erased. I would say go through it. I did 4 or 3 posts on this, on the strange theory of light and matter, 1, 2, 3, and then sort of general appraisal. The velocity is always c, and there are no weird trajectories for a photon. It doesn't sort of curve around and has a speed that's less than c and then accelerate again to a speed above c. That's nonsense. The thing to note is that the spin of this bivector that you have here, which may not be in the right order, the right-hand rule when you apply it, this is a picture from Wikipedia. Let me acknowledge my sources. Normally the magnetic field vector should be in the other direction. I attribute it to people lacking a basic knowledge of mirror symmetry. But yeah, thing where I go for dark matter and dark. But in any case, you're gonna have a bivector, and that's gonna be either in 2 states, where spin states, which is different from energy states. Either this bivector doesn't spin around, or it does. It goes in this direction, or it goes in that direction, and it's plus or minus 1 full or a half unit of Planck's quantum of action. I think it's a full unit of action, because the frequency with which the field vector goes, when it spins around, it also needs to respect that and come back to the original direction of the E vector after a full cycle of oscillation. Yeah, that's the photon model. A photon goes from A to B, and you can immediately see that, you will have a wave function that orbits, that sort of gives the in and out oscillation of the electric field vector, but it will also, let me pull up some images from Wikipedia. Yeah, we have it here. Planarly, planar oscillation. But the more interesting one would be this one, I think. Left-handed or right-handed circularized polarized, or plane polarized in the x direction or in the y direction. And so you have this game of a phase and a phase difference. So the next thing is then the electron goes from some point A to B. I said that B is probably the point where the photon and the electron would meet in this interaction theory. That's very complicated. I have my electron model where I think we have a Zitterbewegung or a naked charge with some size, which is quite sizable in comparison to the Zitterbewegung charge in a proton. That goes around and round and round, and the relations of this charge that oscillates around, we have the radius of the charge itself, which is a fine structure constant times h bar times c divided by the electron energy. We have the Compton radius, which I said in my model, I can imagine that a photon would actually interfere with the enormous magnetic field inside of the ring current that an electron actually is. But is that real? We don't know. All we know is that the radii of this Compton radius and the classical electron is the radius of the naked charge, and the Bohr radius with the various energy levels, n is 1 or 2 or 3 or 4. Simplified for level 1, it's 1 over alpha times the Compton radius. But you do have sort of an interaction, or at least something that should inform the probability of a photon interacting with the naked charge inside of an atom or a molecule or a crystal structure, and that would be something of the order of the fine structure constant squared, because that's the ratio between the naked charge, the classical electron radius, and the Bohr radius. So the model of an atom or a molecular, I mean, even for a simple hydrogen atom, it's quite complicated, and I'm going to show a paper that I'm pretty proud of here, explaining the Lamb shift, where I say basically, when you model electron orbitals, even for a very simple hydrogen atom, you will have at least, you will have 4 quantum numbers. And so when you combine an atom in some kind of molecular structure, show that theory of radiation, copper sulfate. I mean, look at the complexities of a copper sulfate. A molecule where you have many modes of vibration, and so you can imagine how difficult it is to model or assign, quantum numbers to a mathematical approach that incorporates the various modes of oscillation in a system like this. Let me go back to the presentation. I think I presented this. So we can imagine that we have an amplitude or probability which is related to real physical processes for an electron, arriving at some very specific point in time, t at some very specific point in space, x, y, z. So then the third thing that is left is the coupling constant itself. And that's where I'm going, like, that should be easy. And it is what Feynman uses in these lectures, which are the Mautner lectures. I said he didn't review them, or but they are the best sold lectures. And the circumstances were sad. He tried to explain basic quantum mechanics to a lay public. At the same time, Feynman was a big clown in saying that no one understands quantum mechanics. I really don't think he believed that. I believe that the very things I'm talking about are actually what he believed in. He said a coupling constant would be, would have to do with the fine structure constant, alpha squared, or would be equal to alpha, or maybe square root. He talks about direction. of coupling is a photon being scattered in its direction of motion, or do we have, pushback and kinetic momentum that gets reversed and the photon passes back, so the plus and minus sign is there. If the photon and the electron happen to be at the same place and the same time, so what's the probability of interacting? It should have something to do with a ratio of surface areas. So is this the picture then? Yeah, I think it is. The interaction is an interaction between a photon and a charge. So we can add many photons on top of each other and account for phase differences and explain the polarization state of a wave in terms of the polarization state of the photons that make up the wave. So yeah, the consistency with classical explanations, I think, is there. You may disagree. But so yeah, we have a duality of fields and charges, which I think, and that's the main mistake in this popular writing, doesn't really come out. I mean, they talk a lot about particle wave duality. Duality is really of fields and charges. Fields are forces that don't have a charge to act upon, and charges are, what fields are playing with. So my conclusion is that the new quantum theory, it works, and the popular books you will read about it give you an easy handle for understanding the math, but the Born, Heisenberg, or Copenhagen interpretation that the probabilities are not rooted into something physical is BS. I talked for only 20 minutes now, but it's more than enough. I thought I would have spent much longer time on this lecture, but it's not. I recommend again. I mean, that's why I'm doing these lectures. Do read my model of an atom completely, including sort of this Lamb shift that was it has been explained as something like, oh wow, this is not like something that the first generation of quantum physicists could account for. Lamb has, I don't know if I mentioned it here, written an interesting paper at the end of his life. But like many people, Lawrence Bell, they regret and they say like, oh wow, this is not what I meant it to be. Or like the Breuil who said like, my wave equation was not meant to be interpreted in terms of probabilities only. I tried to model the equations of motion, and he did. So there's plenty of stuff like that is out there. My blog is dead at readingfeynman.org. But yeah, have a look at the 3 or 4 posts I made on this one. It did not get how would I say, I'm kind of angry with the censorship that I'm not going to mention his name, but sort of the protector of Feynman's lectures, who has the copyrights, did to my blog, taking it as far to a DCMA takedown notice is something that I don't take lightly. Fortunately, I have family, friends, and they said it's just going to draw more attention to what you are trying to do, which it probably did. But Mr. Gottlieb, I do not like you, and I hope you will rest in peace. And I really don't mean anything, but it's just like, we all try to make sense of the world. And, pushing it as far, using the authority of the MIT to, take down you know, mutilate my 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 blog in which I invested so much. That's kind of something that I don't like, and I don't mind. I don't mind at all. I think you helped me to draw attention to you know, things we should all be aware of, and in any case, you hugely increased the popularity of my papers and whatever is left of my blog. And that's gonna be it. I'm at half an hour, I guess, 25 minutes. So I wish you a very nice evening. Let me scroll through. Yeah, this is something I hadn't mentioned. On QCD, because people ask about it, say, okay, for QED, you know, you did your stuff on, you know, the conservation laws of charge and energy and linear and angular momentum. In QCD, we have different laws. I have this paper, which I didn't put on ResearchGate, but where basically, and I think that's one of the things that bothered yeah, I have this video. I didn't pull it up actually. I know I already did probably. Where Gelman talks about Richard Feynman and their conflicts and whatever. I think Feynman's model of partons was equivalent. He said what he had to say is, you know, if you really want to have like a scattering matrix or a, you know, whatever explanation for how disequilibrium states evolve, and you wanna work with partial charges and new ideas like you know, color charge, then you're gonna have you know, if charge you have plus one, plus a third, minus a third, plus 2/3, minus 2/3. And then you combine it with three colors, you know, that will do the trick. You don't need to invoke what we have here, metaphysical terms like, you know, gluons. And so the quark-gluon model, I think Feynman's, and that's to his credit, his Parton model, which didn't have excited terms like colors or glue or whatever other thing. It did not come. I mean, the quark-gluon model didn't come with any simplifications over his model of partons. So yeah, when you go from black-white television to color television, yeah, RGB, the RGB scheme is a natural one to invoke, and that's what I did. But I think Murray Gell-Mann's critique of Richard Feynman having become a clown or a caricature of himself, or being too much you know, preoccupied with his own personality, is a bit unfair, because I think Murray Gell-Mann was at least as much an ego as Richard Feynman. And you know, watch that video, make up your mind, and that's gonna be it. Let me pull up the tabs to make sure I didn't forget anything. No, I haven't. 30 minutes. I wish you a very nice evening, and this is probably really my my last lecture. I said it's not a typical one. I'm striking back at some people here, and also you know, talking about stuff that would be difficult to write out.